Welcome back to the emergency lecture series. After a long time, I'm restarting the videos. In the coming days, we'll be learning about the ECG. First of all, we'll be learning about electrical activity of the heart, then moving on to the conduction system, and then recording and interpreting a 12-lead ECG, rhythm interpretation, and some abnormalities in very common diseases. So let's come back to electrical activity of the heart. I'm Dr. S. Prakash Babu, Associate Professor of Emergency Medicine. So coming to the anatomy of the heart, you all know heart is a muscular organ that pumps blood. It is located in the middle mediastinum, slightly to the left of the sternum. It's quadrangular pyramid which is foreign to one of its sides. The base faces the posterior thoracic wall and its apex is pointed towards the anterior thoracic wall. You all know that it's divided to 4 chambers. There are 2 upper chambers called the atria and there are 2 lower chambers called the ventricles. The atria are the receiving chambers and the ventricles are the pumping chambers. There is the intraatrial septum dividing the 2 atria, interventricular septum which is the thick muscular septum dividing the 2 ventricles. Atrioventricular septum is a fibrous band of tissue which divides atria and the ventricles and leads to electrical neutrality between atria and the ventricles. Coming to the myocardium. Myocardium is the wall of the heart. It's composed of cardiac muscle cells called the myocytes. Myocytes are separated by intercalated discs and joined by gap junctions. It's a syncytium. You all know what is a syncytium. Syncytium is an endless structure. Because of these gap junctions in the intercalated discs, the whole of the myocardium acts as a single muscle fiber. Syncytium helps in rapid propagation of impulse and a coordinated contraction. Because of the presence of the septum in between the atria and the ventricles, which is the fibrous septum which doesn't conduct electricity, atrial muscle acts as one syncytium and the ventricular muscle acts as another syncytium. So what are the properties of cardiac muscle? Does it have any specific properties? Yes, of course. The most important property is automaticity, which is the ability to generate its own impulses. Then the rhythmicity. Rhythmicity means generating impulses at regular intervals and propagating them. Conductivity is the ability of the heart to conduct electrical activity in the form of action potentials. Contractility is the ability to contract when it is excited by an action potential. Origin of heartbeat. The resting membrane potential of SA node is minus 60 millivolts. Action potential is initiated when it reaches minus 40 millivolts. Decay in resting membrane potential from minus 60 millivolts to minus 40 millivolts is due to slowly reducing outward potassium currents, which causes the action potential spark. Rate of decay of resting membrane potential determines the rate of firing and thus the heart rate. So this is a picture depicting the sinoatrial node action potential. So the resting membrane potential is about minus 60 millivolts. When it reaches about minus 45 to minus 40 millivolts, there is an action potential. During the action potential, there is influx of calcium. It reaches a peak and then comes down because of outward current of the potassium. Once it comes down, touches the baseline, that is the resting membrane potential, there is an aftershoot due to continued efflux of potassium, and then the cycle repeats. Decay of pacemaker potential determines the heart rate. Control of heart rate, how the heart rate is controlled. Normally, it's under the control of the sinoatrial node. So, the intrinsic rhythm of sinoatrial node is the heart rate. When there is sympathetic activity, like by noradrenaline, there is increased heart rate, and when there is vagal activity due to release of acetylcholine, there is slowing of the heart rate. Ventricular electrical activity, resting membrane potential is minus 90 millivolts. See the difference between the resting membrane potential of the SA node, which is less then the resting potential of the ventricles. Threshold potential is also less for ventricles. Threshold potential is minus 65 millivolts. Threshold potential is reached by transmission from conduction system or the adjacent myocytes. The AP curve is same throughout the conduction system. This is the picture depicting the ventricular action potential. This is the interplay of multiple ion channels to cause a ventricular action potential. So in the y-axis, the dominant potential in millivolts is depicted. In the x-axis, the time is depicted. So this is the resting potential. From resting potential, there is slow depolarization, and then a rapid phase of depolarization, which is the phase 1 depolarization. Phase 1 of depolarization is due to influx of sodium and calcium. It reaches a peak, and then there is plateau phase. Plateau phase is the phase 2, wherein there is continued influx of calcium and efflux of potassium. And then there is the rapid depolarization phase, which is due to outward currents of the potassium. Now the calcium channels are closed, so the potential falls back to resting potential, which is phase 3. And then the resting membrane potential is the phase 4. It is caused by leaky potassium channels. The phase between the resting membrane potential reaching minus 45 millivolts, that is the action potential, to the repolarization phase reaching the action potential is called the absolute refractory period. A second action potential cannot be initiated during this time, however large is the potential. Action potentials in other areas. Action potential in atria is similar to ventricles but more triangular and lesser duration. The action potential in Purkinje system is also similar but has a spike at the peak of the upstroke. Atrial cells, AV node, bundle of his, and the Purkinje system also exhibit decaying resting potentials that can act as pacemakers. SA node is the fastest, usually suppresses the others. So dominance or overdrive suppression is the cause for SA nodal dominance. How excitation contraction is coupled? This picture depicts the excitation contraction coupling. There is sympathetic stimulation, increased calcium entry into the cells through the calcium dihydropyridine receptors. This is the voltage operated calcium channel that reaches the tubular SR. From tubular SR, there is increased calcium release. This is called calcium induced calcium release. So when calcium is released inside the cells, there is an action potential spike. The action of calcium potassium ATPase, and then calcium is actually moved out of the cell, either using energy or through calcium sodium antiportal. For every 1 calcium moved out, there are 3 sodium moved into the cell, and then the sodium potassium pump comes into action, moves out 3 sodium and moves in 2 potassium to cause electroneutral. Sodium potassium exchanger, this sodium pump. So let's begin with cardiac conduction system. Cardiac conduction system is useful for generation and conduction of impulses. Formation is formed by specialized muscle cells. Functions as initiator and propagator of the impulses. It contains a pacemaker, a gateway, and various tracts which conduct the impulses. So this is a depiction of the conduction system of the heart. There is SA node, which is located at the junction of the right atrium with the superior vena cava. From the SA node, impulses can directly spread onto the atria and also spreads to the AV node through 3 internodal tracts: anterior, middle and the posterior internodal tracts. As I told earlier, the atria and ventricles are separated by a fibrous septum which doesn't conduct electricity. So the only gateway between atria and the ventricles is the AV node. Okay, so there is AV node, and then there is bundle of his. Bundle of his, as soon as it arises, it divides into a left bundle branch and a right bundle branch. Left bundle branch again divides into left anterior division and left posterior division, also called as fascicles. And then finally, the Purkinje fibers, multiple Purkinje fibers innervate the cardiac muscle cells. SA node is located at the junction of the SVC and the right atrium, acts as the main pacemaker, are generated by dominance. Densely innervated with postganglionic adrenergic and cholinergic nerve terminals, contains a more than threefold greater density of beta adrenergic and muscarinic cholinergic receptors. Internodal and intranodal conduction. Impulse spreads directly to the atria. Three internodal tracts, anterior, middle, and posterior, connect the SA node and the AV node. Impulse travels along the internodal tracts to reach the AV node. Atrioventricular node is located just beneath the right atrium. Endocardium anterior to the ostium of the coronary sinus delays and then relays the impulse, thus functioning as a gateway to affect ventricular systole after the atrial systole. Normal AV nodal delay is 0.12 to 0.2 seconds. Bundle of his and bundle branches. Bundle of his starts from AV node and enters the ventricular septum. This is the only normal connection between the atria and the supraventricular conduction system. It branches into left bundle branch and right bundle branch. Left bundle branch further branches into left anterior fasciculus and the left posterior fasciculus. Terminal Purkinje fibers connect with the ends of the bundle branches to form intervening networks of endocardial surface of both the ventricles, transmit the cardiac impulse almost simultaneously to the entire right and left ventricular endocardium. Thank you.